this episode, we start by looking at a problem that sounds very technical but shows up in surprisingly ordinary ways across modern systems: cryptographic failures. A beginner might hear that phrase and imagine a broken algorithm, a brilliant attacker cracking impossible math, or a scene from a spy movie where someone defeats encryption in seconds. Most of the time, that is not what is happening at all. In the real world, cryptographic failures usually happen because people use protection incorrectly, apply it inconsistently, or forget that the strongest lock in the world does not help if the key is hanging on the front door. That makes this topic important for someone preparing for a security analyst role, because analysts are often not the people inventing encryption, but they absolutely are the people who must recognize when organizations are relying on it badly. Once you understand what cryptography is supposed to protect, it becomes much easier to understand how those protections fail, why the failures matter, and why a system that looks secure on the surface can still expose sensitive information underneath. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. At a high level, cryptography is the discipline of protecting information so that only the right people or systems can read it, verify it, or trust where it came from. That protection can take different forms. Encryption is used to make readable data unreadable to anyone who does not have the right key, while hashing is used to create a fixed fingerprint of data so changes can be detected. Digital signatures can help prove that a message or file came from a trusted source and was not altered along the way. When these protections are working well, they help preserve confidentiality, integrity, and authenticity, even if data travels across untrusted networks or sits inside large shared environments. A cryptographic failure happens when the protection is missing, weak, outdated, misapplied, or managed so poorly that an attacker can bypass it without doing any heroic mathematics. That is why beginners should think of this topic less as a lesson about secret formulas and more as a lesson about security promises. If a system promises to protect data, but the way it uses cryptography does not actually support that promise, then the system has a cryptographic failure. One of the biggest misconceptions is the idea that using encryption anywhere means data is protected everywhere. That is simply not true. A company might encrypt customer data while it travels across the internet, but then store the same data unencrypted in a database backup, a temporary file, or a reporting export. Another organization might use a respected algorithm, but configure it with weak settings, reuse the same keys for too long, or fail to protect the systems where those keys are stored. In both cases, leaders may believe the environment is secure because encryption exists somewhere in the workflow, yet the actual exposure still remains. This is why cryptographic failures are often about gaps between intention and reality. Security is rarely improved just by naming a technology. It is improved by using that technology correctly from end to end. For an analyst, that means asking practical questions instead of assuming protection. Where is the data created? Where does it move? Where is it stored? Who can access it? And is cryptography applied appropriately at every meaningful point rather than only in the most visible place? Key management sits at the center of this subject because cryptography is only as trustworthy as the way keys are created, stored, rotated, shared, and retired. A key is what turns protected information back into readable information. So losing control of a key is often just as damaging as losing control of the data itself. Imagine a company that encrypts an archive of payroll records but stores the decryption key in a plain text file on the same server. On paper, the archive is encrypted. In practice, the protection is almost meaningless because anyone who finds the archive can also find the key needed to open it. Similar problems appear when organizations leave default keys in place, fail to replace keys after an employee departure, or keep using the same secret for years because changing it feels inconvenient. These are not rare mistakes made only by reckless teams. They happen because key management is less visible than shiny security products, yet it is fundamental to whether cryptographic protection is real. When analysts review risk, they must learn to see key exposure, poor storage, weak lifecycle practices, and sloppy access control as major findings rather than minor housekeeping issues. Password storage is another area where cryptographic failures show up in ways that deeply affect real people. New learners sometimes assume a website keeps your password in a recoverable form and simply checks whether what you typed matches what it already has. Well-designed systems should not work that way. Instead, passwords should be transformed using strong hashing methods so the original password is not stored in readable form. Even then, proper salting and careful design matter, because weak hashing choices or reused values can make large-scale password cracking much easier after a breach. If an attacker steals a password database and the passwords were stored plainly or with poor protection, the damage spreads far beyond one application, since many users reuse passwords across different accounts. That is why cryptographic failure is not just a technical defect buried in the background. It can become identity theft, unauthorized purchases, fraud, business disruption, and a loss of trust that follows users long after the original incident. An analyst should hear password storage discussions and immediately think about hashing strength, salt usage, breach impact, and how quickly a weakness could cascade into broader compromise. Data in motion creates another major category of failure because organizations often assume that any web traffic is protected equally. A secure connection depends on far more than a lock icon or a familiar browser indicator. Hypertext Transfer Protocol Secure, HTTPS, and Transport Layer Security, TLS, are meant to protect information as it moves between systems, but weak versions, weak ciphers, invalid certificates, or inconsistent implementation can reduce that protection dramatically. In some cases, sensitive pages may load securely while supporting content or background requests use weaker paths. In other cases, an application may allow people to fall back to insecure connections, exposing sessions or credentials to interception. Older technologies such as Secure Sockets Layer, SSL, also remind us that cryptography ages and protections that were once considered acceptable can become dangerous as attacks improve and standards move forward. For a beginner, the key lesson is that transmission security is not a yes or no question. It is a question of whether modern protections are fully enforced, properly maintained, and consistently applied wherever sensitive data travels. Certificates add another layer that beginners often overlook because they seem invisible when everything is working normally. A certificate helps systems establish trust during secure communication by proving identity and supporting encrypted connections. If certificates are expired, issued by the wrong source, mismatched to the system they claim to represent, or handled carelessly, users and services can end up trusting the wrong destination or failing open in unsafe ways. This is especially dangerous because many people are trained by habit to click past warnings instead of treating them as meaningful signals. The deeper issue is that trust on a network is not automatic. It has to be established and maintained, and cryptography plays a major role in that process. When certificate handling becomes sloppy, attackers may be able to impersonate services, intercept communications, or create confusion that leads users to accept unsafe behavior as normal. From the analyst perspective, certificate problems are not cosmetic annoyances. They are signs that the organization may be weakening the very trust model that secure communication depends on. Randomness may not sound like a security concept, but it matters enormously in cryptography because many secrets must be unpredictable to remain useful. Keys, session identifiers, password reset tokens, and other values lose much of their protective value if they can be guessed or generated in a predictable pattern. A system that creates secrets using poor random number generation may look secure at first glance, yet still allow attackers to anticipate future values or replay valid ones. This is a subtle kind of failure because the protected data may still be encrypted and the interfaces may still appear polished, while the underlying unpredictability is missing. Good cryptography depends not only on strong algorithms, but also on strong entropy, meaning enough unpredictability in the inputs that attackers cannot model or reproduce them. Beginners do not need to master the mathematics of randomness to understand the risk. They only need to recognize that predictable secrets are weak secrets, and weak secrets can quietly turn a supposedly protected environment into one that is easy to exploit without much noise or obvious breakage. Another common issue appears when developers or administrators hardcode secrets into software, scripts, templates, images, or deployment files. This turns cryptographic protection into a false comfort because the secret exists, but it is sitting in places where too many people or systems can discover it. A shared application secret placed inside source code may spread to test environments, backups, archive packages, and developer workstations. Years later, even after teams change, that same secret may still exist in forgotten copies across the organization. Attackers know this, which is why exposed keys and tokens are so valuable during intrusions. They can unlock data, support impersonation, or allow movement across connected services without the attacker needing to defeat the cryptography itself. For security analysts, this is a useful mindset shift. A cryptographic failure does not always mean someone broke the algorithm. Sometimes it means defenders treated a secret like ordinary text, and once that happens, the protective power of the cryptographic design starts to collapse no matter how strong the underlying math may have been. Misuse of cryptography also happens when teams try to invent their own protective approach instead of relying on well-understood practices. New learners sometimes assume that adding extra complexity makes a system safer, but homegrown protection can create fragile designs full of hidden weaknesses. A developer might combine several transformations and believe the result is stronger because it feels unique. Another team might encrypt data but skip integrity protection, meaning an attacker cannot read the information directly but may still be able to alter it in damaging ways. Others may reuse keys across different purposes, fail to separate testing from production, or continue using outdated modes simply because the application still appears to function. These problems matter because cryptography is one of the areas in security where being clever is often more dangerous than being disciplined. Reliable protection usually comes from proven standards, careful implementation, and conservative handling of secrets. When organizations improvise instead, they often create systems that seem sophisticated internally, but fall apart quickly once an attacker begins probing the assumptions behind them. Real-world examples make this topic easier to understand because cryptographic failures often hide inside everyday business processes rather than dramatic breach headlines. Think about a healthcare organization that protects patient data in its main application but emails spreadsheet exports without adequate protection to support teams. Consider a retailer that secures customer checkout traffic yet keeps old card-related reports in unprotected storage. Picture a company that retires an older web service but leaves its certificates, service accounts, and encryption keys active in connected systems long after the service itself is forgotten. In each case, the failure is not one isolated technical flaw. It is a mismatch between where the organization thinks protection exists and where protection is actually maintained. That is why analysts must pay attention to the full data lifecycle rather than only the moment when a user submits information. Data gets copied, cached, synchronized, archived, restored, and reused for business reasons. Every one of those moments can create a new cryptographic exposure if protection does not travel with the data or if old secrets remain valid long after they should have been retired. For someone studying for this exam, it is useful to connect cryptographic failures to the daily work of analysis and vulnerability management. Analysts may encounter findings related to weak protocols, missing encryption, expired certificates, exposed keys, unsafe password storage, or applications that transmit sensitive data too openly. The important habit is not merely to label these items and move on. It is to understand what business asset is affected, what type of data is at risk, how easy the weakness would be to exploit, and what the likely consequences would be if an attacker succeeded. A missing control around a public brochure site is very different from the same weakness on a payroll platform, a healthcare portal, or an identity system. Analysts also need to remember that cryptographic failures can be hidden dependencies. A problem in one supporting service may quietly undermine many applications that trust it. Strong analysis therefore connects the technical issue to the trust relationships, data flows, and operational impact that surround it, rather than treating the finding as a narrow configuration detail with limited meaning. It is also important to separate common myths from sound thinking. Strong cryptography does not make a weak system automatically safe. Encryption does not excuse poor access control, careless logging, weak software design, or uncontrolled data sprawl. At the same time, a cryptographic failure is not always catastrophic in exactly the same way, so analysts should avoid exaggerated reactions that ignore context. The practical question is what the weakness allows an attacker to do, how much effort it would take, how long the weakness has existed, and what assets or identities it could expose. That balanced mindset helps organizations prioritize wisely. Some failures demand immediate escalation because they expose passwords, payment data, customer records, or trusted communications. Others still matter but can be addressed through planned remediation if the surrounding risk is lower. Security work improves when teams move past magic thinking on one side and panic on the other. Good judgment comes from understanding that cryptography is a powerful control, but only when it is part of a broader security approach grounded in disciplined implementation and realistic risk evaluation. By the time you recognize these patterns, cryptographic failures start to look less like mysterious technical edge cases and more like predictable breakdowns in trust, lifecycle management, and design discipline. The central lesson is simple even if the underlying science is complex. Data is not protected because someone says it is encrypted, and trust is not established because a secure symbol appears on a screen. Protection depends on choosing appropriate methods, handling keys carefully, storing secrets properly, maintaining modern protocols, validating identity, and applying safeguards consistently everywhere sensitive information lives or moves. That is why this topic matters so much to new security analysts. You may never be asked to invent a cipher, but you will absolutely need to notice when an organization is relying on cryptography in a way that only looks safe from a distance. When you learn to spot those gaps early, you help reduce the chance that everyday mistakes become serious breaches, regulatory problems, financial loss, or lasting damage to user trust.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.